Hey guys, this is Craig Enders, and thanks for tuning into the Blimp video channel. In other videos, I've mentioned that Blimp uses an iterative algorithm called Markov Chain Monte Carlo, or MCMC. In this video, I'm going to talk about evaluating the quality of MCMC estimation. So I'll show you how to determine whether MCMC is converged, how many iterations to specify, and then how to address problems when they arise. Before we get started, I want to thank the Institute of Educational Sciences for their support and point you to the project's website. You can download Blimp from the same homepage. Let's start with a quick overview of MCMC estimation. Broadly speaking, MCMC consists of two steps. First, Blimp estimates a series of regression models using the filled-in data. Next, it uses those resulting model parameters to construct distributions of missing values from which it samples updated imputations. These two steps are repeated thousands of times. By default, Blimp invokes two MCMC processes or chains using different starting values. We need to divide the MCMC chains into two segments. The first segment is the warm-up or burn-in phase that allows the algorithm to converge to parameter values that are optimal for the data. The software discards the estimates from the burn-in phase. The second segment is the analysis phase that generates the parameter estimates that we use for inference. We need to specify the number of iterations in both of these periods when we use the software. As an example, suppose we want a warm-up period of 5,000 iterations and we want to use 10,000 estimates after that to describe the parameter distributions. Taking a look at the Blimp syntax on the left, the burn command specifies the number of warm-up or burn-in cycles completed by both chains. The iterations command specifies the number of parameter estimates for the final summaries. Those 10,000 estimates are distributed equally across the two chains. The diagram on the right shows a schematic of the MCMC algorithm. The key thing that we want to address in this video is how to decide the number of iterations in each of those two periods. I want to start with the burn-in period first. As I mentioned, Blimp runs two MCMC processes in parallel from different starting values. We want the burn-in period to be long enough that the estimates can escape the gravity of those initial starting values, but we also want the estimates to stabilize in some sense. The potential scale reduction factor is a simple diagnostic that we can use to evaluate MCMC convergence. An important feature of MCMC estimation is that parameters randomly vary from one iteration to the next. MCMC generates plausible parameter values by sampling estimates from distributions. For example, MCMC usually samples means and regression coefficients from normal distributions, and it samples variances from right-skewed inverse gamma distributions. The trace plots on this slide show parameter estimates from the first 50 cycles of an MCMC run. The estimates come from a simple regression model with an intercept, slope, and residual variance. Each dot in the time series is an estimate, and the curves on the right are the parameter generating distributions. Over a large number of iterations, we want the estimates to oscillate around a stable center line, the value of which is our MCMC point estimate. MCMC is really different from maximum likelihood estimation because it doesn't converge on a single set of parameter estimates that maximize fit to the data. Rather, the goal is to generate an entire distribution of plausible parameter values that could have produced our data set. MCMC converges when those parameter distributions become stationary. In practical terms, that means that the estimates oscillate around a stable center line, and then the spread of those oscillations is stable or doesn't change as we increase the number of iterations. A minute ago, I mentioned that Blimp defaults to running two MCMC chains in parallel. The potential scale reduction factor is going to assess the stability of the distributions by comparing the estimates from those two chains. Let's take a look at the conceptual formula for the potential scale reduction factor. The formula has two components, mean difference variation and within-chain variation of the estimates. Numerically, the diagnostic treats the two MCMC chains as a grouping variable, and it uses mean squares equations from ANOVA to calculate the two sources of variation in the estimates. First, let's look at mean difference variation. The two graphs are time series plots that display estimates from the first 200 iterations of two MCMC chains. What you notice from the graphic is that the estimates from the two chains oscillate around very different mean values. Ideally, this mean difference shrinks towards 0 the longer MCMC iterates, and the between group term in the equation vanishes or gets close to 0. In contrast, within chain variation quantifies the degree to which the estimates vary around the chain's average. The within chain variation doesn't go away because the estimates will continually change as long as MCMC iterates. However, that variability should stabilize and the two MCMC processes should produce similar parameter variation. Looking at the equation, when the mean difference variation shrinks towards 0, the within chain variation in the numerator and denominator cancel out, and the equation reaches its theoretical minimum value of 1. Recommendations from the literature suggest that the potential scale reduction diagnostic value should be less than about 1.10 or 1.05. I usually adopt the more conservative cutoff of 1.05. We have evidence that MCMC is converged when separate chains give estimates with the same means and spread. The graph on the left depicts a situation where MCMC has not yet converged because the two chains are producing very different average parameter values. The graph on the right depicts a situation where MCMC has converged because the two chains produce very similar average parameters. Every parameter in the model converges at a different rate, and each parameter also has its own unique PSR diagnostic value. Blimp divides the burn-in period into 20 equal intervals, and it pauses at the end of each interval to compute the PSR diagnostics for every parameter. To summarize that information, the software prints a table that has the worst or highest diagnostic values at each of those 20 steps. To illustrate, I'll use data from an educational intervention designed to improve math problem-solving skills. The analysis model is a multiple regression where post-test scores are regressed on pre-test scores and a binary intervention indicator. At this stage, I'm going to focus on diagnosing convergence. As an initial guess, I often start with a 5,000 iteration burn-in period. For now, I'll just set the number of post-burn-in iterations to 10,000. As I mentioned, Blimp computes diagnostics for every model parameter 20 times throughout the burn-in period. It displays the highest or worst values in a column labeled highest PSR. What we care about is whether MCMC is converged by the end of the burn-in period. Looking at the bottom row of the table, we see that a 5,000 iteration burn-in period was more than enough because the worst PSR index across all models was well below 1.05. Although I could shorten the burn-in period if I wanted to, there's no reason to do that. That example was pretty much the best case scenario because all of the model parameters converged very quickly in the iterative process. I want to show you a different situation where MCMC doesn't converge so quickly. Continuing with the data from the educational intervention, the analysis model is still a multiple regression, but this time I'm using an ordinal self-efficacy variable as a covariate. Note that this is a 6-point rating scale, so I define the variable as ordinal on the ordinal command line. The burn-in iterations is still set at 5,000. Looking in the last row of the table, the highest potential scale reduction factor is above the 1.05 threshold. This tells us that MCMC has not converged after a 5,000 iteration warm-up period. The solution is straightforward. All we need to do is simply increase the burn-in period. Before we increase the number of warm-up iterations, I want to show you how to get a full summary table of every diagnostic value in the model. Revisiting that previous table, the rightmost column gives a numeric index for the parameter with the highest potential scale reduction factor diagnostic. The table tells us that parameters 17, 18, and 19 are producing the high diagnostics. To see which parameters we're talking about, we need to make a small addition to the script. The syntax is the same as before, but I've added the options command and the labels keyword. This will print out a full summary table that has the PSR diagnostic for every parameter in the model. The output now includes an additional table titled Parameter Labels. The numeric indices in that previous table are now listed in the first column. The 5 columns to the right display the PSR values at just 5 of the 20 checkpoints during the warm-up period. We can see here that the focal model parameters are not the issue because their PSR values are all near the minimum value of 1. Blimp automatically estimates the supporting models needed to fill in the missing values of the incomplete predictors. Scrolling down the output, we find that indices 17, 18, and 19 are associated with threshold parameters in the self-efficacy model. Because this variable is ordinal, this is a probit regression where the thresholds are z-score cut points that divide an underlying latent response variable into discrete segments. 3 of the threshold parameters have elevated PSR diagnostics at the final iteration of the burn-in period. Again, that's not a surprise because we know from the MCMC literature that threshold parameters generally require longer burn-in periods. Usually all we need to do to address those high diagnostic indices is to simply increase the number of burn-in iterations. As a simple rule of thumb, you could just double or triple the number of warm-up iterations. Going back to the Blimp script, I doubled the warm-up period from 5,000 to 10,000 iterations. Don't be afraid to go much higher because very complex models might require longer burn-in periods. Looking at the last row of the diagnostic summary table, the worst or highest PSR value is now well below the 1.05 threshold. Now that we've dialed in the warm-up period, we need to determine the number of iterations for our final analysis. In those previous examples, I set the number of post-burn-in iterations to 10,000 because in my experience, that's usually an adequate value. To verify that setting, we can look at a diagnostic called the effective sample size or the effective number of MCMC iterations. This is the summary table from the focal regression model. The rightmost column is the effective sample size diagnostic. The N effective values are essentially measures of autocorrelation. Larger values mean that the 10,000 parameter estimates contain a lot of non-redundant information, whereas smaller values mean that estimates are redundant due to that autocorrelation. As a rough rule of thumb, the Gelman et al. Bayesian statistics book suggests that a minimum value of 100 is often sufficient. With that as our guideline, the focal model estimates look just fine. This slide shows the summary table for the ordinal self-efficacy predictor. In this case, the effective sample size diagnostics for the threshold parameters are a bit low. The low values suggest that these parameters have substantial autocorrelation from one iteration to the next. To be on the safe side, we probably want to tweak the MCMC settings to get those diagnostic values a little bit higher. Again, a simple rule of thumb would be to double or triple the number of post-burn-in iterations. Going back to the script, I doubled the number of post-burn-in iterations from 10,000 to 20,000. Again, don't be afraid to go higher because complex models might require more iterations. After increasing the number of iterations to 20,000, the effective sample size diagnostics look just fine and all are above the 100 threshold. The process I just demonstrated works most of the time, but there may be rare cases where MCMC doesn't converge even when you set the number of iterations to a very high number. In my experience, even complicated models usually don't require more than 100,000 iterations. If the diagnostic indices don't fall into place by then, it usually means that there's a problem with the data. The data might lack information necessary to estimate some part of the model. Next, I want to backtrack and talk about a common cause of MCMC estimation problems and then show you a simple way to fix those issues. This script is from an analysis that uses a 9-point ordinal self-efficacy measure as the outcome. I started with my initial recommendation, which is to set the burn-in period to 5,000 iterations. After seeing that the model didn't converge, I continually increased both iteration values to 50,000. Looking at the last row of the PSR summary table, the worst or highest diagnostic value is trending in the right direction, but it's still well above the 1.05 threshold. For me, that's a red flag because 50,000 iterations is very high for such a simple model. Similarly, the effective sample size diagnostics for the threshold parameters are very, very low. These low values are caused by high autocorrelations, but those autocorrelations themselves often signal that the data don't contain the information necessary to estimate that part of the model. When MCMC is struggling to converge, my experience is that this is almost always due to a sparse discrete variable with few observations in one or more of the categories. So this is the first place that I would look to diagnose problems like we're seeing in the previous analysis. This is a frequency distribution of the 9-point self-efficacy variable. Notice that the lowest two categories each comprise fewer than 1% of the observed responses. In this case, there's simply not enough data to estimate those threshold parameters. The best option would be to create a new 6-point variable that collapses the bottom three categories. To address the problem, we need to recode the original 9-point variable into a new 6-point rating scale. Here I take the lowest three categories and recode them into a single category. The table on the right shows the collapsed 6-point rating scale. As a rule, it's a good idea to inspect frequency distributions and crosstab tables for every discrete variable or pair of discrete variables in your model. Collapsing categories can be especially useful with multi-categorical nominal variables where some of the subgroups have very low cell counts. However, there may be situations where even after collapsing variables, you still have convergence issues. To illustrate, let me show some crosstab tables from a recent user support email. These are a pair of crosstab tables from a model with several incomplete binary predictors. Looking at the table on the left, X2 is itself very sparse with only 48 out of about 700 observations in the no or zero category. When you cross that variable with X1, you end up with a 0 cell count. Blimp's default model for those incomplete predictors won't converge because the bivariate association between X1 and X2 is inestimable. Although it doesn't have empty cells, the table on the right exhibits a similar problem because it also has very few observations in one of the subgroups. Again, patterns like this account for the vast majority of convergence issues related to missing data in my experience. By default, Blimp automatically estimates the supporting regression models needed for missing data handling on the incomplete predictors. These supporting models include all possible associations among the predictors. When we have sparse crosstab tables like the ones from the previous slide, what we need to do is override that behavior and manually specify those models. What we need to do is separate the two problematic predictors so that the model no longer contains their correlation. To illustrate, suppose we have two binary predictors like before, x1 and x2, and a continuous predictor z. The simplest way to specify the model is to regress y on the three predictors like I show here. Although the predictors are incomplete, we don't have to specify models for them because Blimp does that automatically. Importantly, those supporting models include every possible association among the predictors. The path diagram on the right shows these correlations as curved arrows. The empty cell in the crosstab table forces us to omit the association between x1 and x2 in the supporting models. I do this by specifying a regression equation for each problematic predictor, in this case x1 and x2. The model section now includes two additional regression equations where x1 is regressed on z, as is x2. The important feature of this specification is that x1 and x2 have no residual association after controlling for z. That assumption may not perfectly match reality, but allows us to include both variables in the analysis. More complex models with many predictors may require some trial and error to identify which covariates we can put on the right side of each regression equation, but the strategy nevertheless scales. Again, inspecting bivariate crosstab tables for every pair of categorical variables is usually a good starting point because that usually reveals the source of the problems. That concludes our brief introduction to evaluating MCMC estimation quality in Blimp. A detailed user guide is available by selecting the Help option within the Help pull-down menu of the graphical interface. That user guide has an entire chapter devoted to the diagnostics that I talked about in this video. Thanks again for tuning in, and I hope you check out other videos.